Thank you very much for joining me again. And today I'll be doing the FS Academy Interceptor. So this would be like a flight training video, learning to fly. So I'm going to do some navigation exercise and a partial panel, meaning when in an emergency, if some of your panels are not working, then you have to try and figure out how to navigate. So right now I'll do this navigation exercise. And again, this is from the FS Academy Interceptor, and that's available in the Microsoft Flight Simulator as an add-on. So yeah, in the marketplace, you can find it. And I've used these before, and they're normally pretty good. There's some issues here and there, but for a training aid or learning aid, this is a very good tool to use. So I would recommend, if you want to try it, go ahead and take a stab at it, or try it and see how it works for you. So let's go ahead and click on that navigation exercise. And we're in our lovely Cessna 152, you know? That's the Rolls Royce of the air, if in a sarcastic way, but hey, it works, it flies. All right, so let's go ahead, read the overview. Solidify your new knowledge in this simple beacon to become IFR, beacon IFR exercise. We will navigate to both NDB and VOR stations to reinforce what we have covered so far. So I was doing some of the trainings earlier, so hopefully I retained it and I can use it, but it's VOR, it's not that bad. So yeah, let's go ahead and try this. Ready to fly.
Hopefully you are by now experiencing firsthand how flying on instruments alone can be broken down to a series of simple techniques. Now we combine the topics covered so far in an en route navigation exercise involving attitude flying plus VOR and NDB navigation. Firstly, tune and identify the Jersey VOR into the NAV1 radio, frequency 112.2.
112.2. So yeah, this is a little bit tricky, being that I am also trying to maintain steady level flight, and (112) and then 0.2. All right. And I have to switch it. Navigation ident on. So I have to go over to
maintain 2,000 feet.
My yeah, let's go over.
Maintain 2,000 feet.
Nav1 ident on. So what am I doing wrong? Oh no. I wish there was a way to repeat the exercise because I totally am losing something here. Okay.
Jersey VOR identified. You can turn off the nav1 ident now.
Okay.
Now, using the OBS, set and intercept the radial 360 to the VOR. We're flying a radial towards a beacon, so remember what this means for the course we need to set.
So he said I think I lost what he said. 3, 2, 1. Okay. I don't remember what he just said, but I think it's 3, 2, 1. So let's go to 3, 2, 1 VOR. Whoa.
Maintain 2,000 feet.
Yeah, this is really annoying. Yeah. All right.
Maintain.
I am at fault for this one. This is all my fault. So I have to do a quick restart on this because I lost some instruction and I'm not oriented properly because, yeah. That was my fault. Yeah. You just got to get this thing set up real fast. And I don't need to zoom in so much. That was the problem because I didn't have a peripheral
Hopefully
view.
you are by now experiencing firsthand how flying on instruments alone can be broken down to a series of simple techniques. Now we combine the topics covered so far in an en route navigation exercise involving attitude flying plus VOR and NDB navigation. Firstly, tune and identify the Jersey VOR into the nav1 radio, frequency 112.2. 2,000 feet.
112.2. Okay. I have to go back to west and
Maintain 2,000 feet.
okay.
Jersey VOR identified. You can turn off the nav1 ident now. Now, using the OBS, set and intercept the radial 360 to the VOR.
360.
We're flying radial towards a beacon, so remember what this means for the course we need to set.
Okay. 360, which is north. Yeah. That works now. All right. Hey, thank you guys for joining. I really appreciate it. If you have any feedback, let me know. But I'm also locked in trying to follow these instructions. So if I don't respond immediately, I'm not ignoring you. Yep. So, all right.
Remember that we are flying a radial to the station, so we use the reciprocal. In this case, that would be a course 180.
So 180.
Maintain 2,000 feet. So
I'm flying away. So yeah.
Maintain 2,000 feet.
Okay, I made a mistake here. So I should have set it to 180. Because I want to go north, so I have to set it to 180. I have to trim better. Yeah, that was okay. So, yep, 180. That's where I need to go.
Maintain 2,000 feet.
I know, buddy. I'm trying to do this while I have to look on the screen and get this thing down. 180. Come on. Almost there. So, perfect. 180. Alright, there we are.
Good. We are flying a radial to the beacon, so we set the reciprocal, course 180.
Perfect.
We can see that with our OBS set, the CDI bar is off to the right. Now turn to a suitable 45-degree intercept heading for a course 180. Maintain 2,000 feet.
Okay. I have to intercept this thing again.
We're looking for a left turn to heading 225, a 45-degree intercept for radial 180.
Okay.
Maintain 2,000 feet.
225.
The CDI was off to the right with our course set, so we chose an intercept heading to the right of our OBS course. Now complete the interception and fly us to the VOR. Maintain 2,000 feet.
Okay. And then head to 180. There we are. Bingo. So now I go to 180.
Maintain 2,000 feet.
Alright, alright.
Follow the course 180 to the VOR and climb to 3,500 feet.
3,500.
Power settings.
There we go. There we are. I have to go to 3,000 feet, so I have to climb 3,500 feet. I'm trying to intercept the view.
To hold a 7.5 degree pitch attitude in the climb.
I have to pitch up.
Make sure to hold a 7.5 degree pitch attitude in the climb.
All right. All right, this is better, way much better zooming in on the panel. All right, we're approaching 2,800 feet, and we're dead center, almost dead center. All right, so let's go back and fly, make sure we're directly south. All right, there we are. So we're climbing steadily, and we have a pitch angle of around 7.5 degrees as requested by my instructor. All right. So I'm following the attitude indicator, and this is right here, the attitude indicator here. And I'm at 3,250 feet, going on to 3,500. And let's reduce the power once we're there to make sure we don't go above.
Now maintain 3,500 feet to the VOR. Continue on the course 180 to the VOR. We'll leave on the radial 200.
We're going to leave on a radial 200. All right. Okay, I'm veering off course. I have to center. Thank you very much for the like. I really appreciate it. Thank you so much.
I wanted you to maintain the course 180, but I see that the CDI is drifting.
I have to maintain the CDI. Hey Krishna, how are you? Thank you for joining. I appreciate it. And I'm just doing these this little exercise to make sure that I follow the instructions. Oh no, I drifted off the wrong direction again.
I wanted you to maintain the course 180, but I see that the CDI is drifting.
Alright, I'll fix it, I'll fix it.
We're getting close to the VOR now. When you enter the cone of confusion, turn right to heading 200.
Okay. Alright, I'm on it. Okay, I'm in the cone of confusion right now. And I'm gonna go to 200. Okay.
We are now aiming to follow the radial 200 from the VOR. Set the OBS to course 200. Great, now let's see if we've intercepted the radial 200. CDI not quite centered on rollout. Make a heading adjustment to center the CDI bar.
Almost there. I'm almost on the...
We're right on course. Continue along the radial 200 at 3,500 feet.
Okay. Alright, that wasn't bad at all. There we are, we're centered now. Sometimes you have to do a little adjusting or correction. Oh no. So all these instructions I am just following just to make sure I can execute. So from the VOR and to and from the VOR, that's a navigational
Now
tool.
we'll look at NDBs. Tune Jersey NDB, frequency 329. You can
So-
assume the NDB has been identified.
329 is the Jersey NDB, so I'm tuning that right now.
Now start a descent to 3,000 feet, again with standard pitch and power.
$3,000 feet. I need to descend. Descending.
Now also start a right turn to heading 270.
Start a right turn to 270.
Level off at 3,000 feet and keep us turning to heading 270.
I'm at 270. Oh,
Now turn and fly us directly to the Jersey NDB, maintaining 3,000 feet to complete the exercise.
all right. Okay. All right. I had to use the NDB needle right here. So that's the NDB needle, and I have to maintain 3,000 feet. There we are.
We want to be at 3,000 feet.
Okay. This needle is a little bit tedious.
We want to be at 3,000 feet.
Okay. I am currently a little bit above 3,000 feet.
This exercise was a review of everything we've covered so far.
Okay.
Next time we will explore IFR system failures, known as partial panel.
All right.
Think about trying this lesson again before we progress deeper into IFR, as it's important to have a solid foundation.
What are you trying to say? All right. Okay, good. Thank you. All right. I got a basic C passing. I was all over the place. All right. Improvement needed, but it's fine. So I'm going to move on to the next activity. In the next activity, let's scroll down. We're going to use partial panel. So the partial panel... Wow, that was pretty loud. But we're going to learn to deal with equipment failures whilst flying, IFR. You can compensate for those loss of certain instrument, but must recognize the symptoms to correctly diagnose the issue. So this is a little bit challenging. So let's get this done. Make sure I have everything set up. All right.
So far, we've been operating a fully serviceable aeroplane. But a crucial skill to possess is the ability to remain in control in the event of an instrumentation failure. In terms of instrument flying, the scenarios most relevant to us are failures to the systems which supply our instruments. There are broadly three sources that drive our cockpit instruments: electrical, pressure, and vacuum. The electrical system drives many of our aircraft systems, such as the lights, radio, and flaps. The turn coordinator is supplied by the DC electrical system, as specified on the face of the dial. If electrical power were to be lost, the wings of the white aircraft symbol at the center of the turn coordinator will return to wings level, and a red flag will be displayed. As we know our rate 1 bank angle and use the attitude indicator to set it, a loss of the turn coordinator is only a minor failure. Of course, the liquid of our balance indicator is unaffected and remains operational. Some of our instruments are supplied with air pressure provided from the outside via two intakes, the pitot tube and static port. The altimeter, VSI and airspeed indicator are supplied with static pressure, which is the outside air pressure. The ASI is unique in that it is also supplied by the pitot tube, which receives the pressure of the oncoming airflow for the ASI to display as our indicated airspeed. In the case of a pitot blockage, the ASI is starved of this oncoming airflow and will display a 0 indication. By maintaining our attitude targets and a suitable power setting, we can be confident that we are flying a safe airspeed.
Yeah.
Use standard power and attitude settings as usual and make a left turn to heading 125 and see how our airspeed remains around our expected 90 knots. Try to maintain 3,000 feet.
We're turning to 125.
Try to maintain 3,000 feet. Try to maintain 3,000 feet. Now let's unblock the pitot and reveal our airspeed. We have around 90 knots on our ASI, as we hoped.
Okay, perfect.
Now let's look at the static system. The static port supplies our instruments with the outside air pressure. This drives the altimeter, VSI, and also supplies the ASI to help correct for altitude. Should the static port become blocked, we would lose altitude information, which is critical to safe flight. Set full power and start a standard climb. See how our altimeter remains frozen at the value it had when the failure occurred, and the VSI shows 0. Our ASI also does not correct for altitude, so it becomes inaccurate. Most aircraft have a selectable alternative source for static air, but this Cessna 152 does not have that option.
Doesn't.
Instead, we can smash the glass of the VSI to allow cabin air into the static system via the VSI itself.
Oh.
We see our altimeter comes back to life. We will no longer have a VSI, but this was a worthwhile sacrifice. When using the alternate static source, we do suffer some loss in accuracy, as the pressure is taken from a less ideal location on the aircraft, usually from somewhere within the cabin.
Okay.
With no VSI, we can no longer use our 10% of vertical speed anticipation method for levelling off at an altitude. Instead, we can revert to a more simplistic method of beginning our level off with 50 feet to go, which is what we would normally expect for this aircraft. Climb to 4,500 feet, starting to lower the nose to the horizon with 50 feet to go, as usual.
Okay.
Keep your pitch attitude set at 7.5 degrees, as usual.
Climbing to 4,500 feet.
Keep your pitch attitude set at 7.5 degrees, as usual. Keep your pitch attitude set at 7.5 degrees as usual.
Okay, I'm doing that, buddy. And 4,200 climbing to 4,500.
Keep your pitch attitude set at 7.5 degrees as usual.
Okay, I'm doing that. All right. $4,300 feet and climbing, and I'll begin to level off a little bit.
Now smoothly set the straight and level attitude. Build the speed back up to 90 knots and then set cruise power. Normally we would aim for a 0 VS on the VSI, but as this instrument is not available, simply set the straight and level pitch attitude. We have so far seen the effects of a loss of our tone coordinator, ASI, altimeter and VSI. The other source to our instrumentation on this type of light aircraft is the vacuum system. A vacuum pump provides suction which powers the gyroscopes that drive the AI and the heading indicator. Should this suction become too low, the gyroscopes would topple and the AI and heading indicator would become unreliable, slowly drifting away from a correct indication. See the suction indication displayed on a small indicator located beside the AI. We will fail the vacuum pump now. Watch for a drop in suction.
Uh-oh.
Note that the suction has now fallen. This means that the AI and the heading indicator gyroscopes will begin to slow. Of particular importance is to note how we do not lose AI indications immediately. There is a red failure flag on the AI, but this only appears once the gyro has begun to topple significantly. So the first clue of a suction loss may be only a slightly toppled AI, showing a pitch or bank change of just a few degrees, which could be difficult to detect right away. Trying to keep a failed AI appearing straight and level can easily cause a large and dangerous bank and pitch input. This would cause large and confusing direction and altitude changes, leaving you unsure which instruments to trust. Remember these points and look to the suction indicator if doubt starts to arise.
Oh, wow.
The heading indicator is also supplied by a suction-driven gyroscope. Rather than rotating to a misleading heading, it will simply stop responding and will remain frozen on its previous value. We replace our heading indicator with our magnetic compass, which we will look at in the next lesson. See how your altitude's drifted? It's more difficult to maintain altitude without a VSI. We compare.
You are a piece of crap. Oh, man. Alright. That's how important those instruments are. Alright, so I'm gonna go back and I'm gonna do the second one. I completed it. He was about to dismiss me. I'm not gonna do it again. Alright. And I'm gonna do the partial panel 2. This is a second part of the partial panel. So all right, so let's go ahead and
we will now look at how we can continue to navigate after a failure of our heading indicator. Remember that your heading indicator is broken and should not be used for this lesson. We have an alternative means of determining our heading, and that is with the magnetic compass, found at the top of our windshield.
well, I don't see one.
The
Okay.
compass is subject to a range of indication errors, depending on factors such as speed changes and bank angle. So let's get to grips with the techniques we will need to make compass turns. Firstly, we will discuss UNOS, undershoot north, overshoot south. This simple acronym represents how we deal with compass turns to headings near north or south. During a turn either left or right towards north, as we pass an actual magnetic heading of north, the compass will underread by around 30 degrees. This means that to roll out on heading 360, we stop our turn when the compass indicates that we still have 30 degrees to go. For example, to turn right onto heading 360, we level our wings as the compass indicates 330. Turning left onto north, we roll out as we see 030 on the compass. We undershoot north. Let's try this. Use the compass to make a left turn now to heading 360. Level the wings once the compass indicates 030. Try to maintain 3,000 feet during this exercise.
Three 360. We're at 030 coming up to 020. And we're going to level out a little bit. Let it keep coming around. And right about now, we're a little bit off. There we are. Come on. We're gonna overshoot. There we go. What? Anyways. What? Yeah, I'm going back the other way.
Now roll wings level.
Okay.
We're not quite on heading north. Make a small heading adjustment. Try to maintain 3,000 feet during this exercise.
Working on it. Thank you guys for being patient. And I'm totally off.
Try to maintain 3,000 feet during this exercise. We are rolled out on heading 360. The undershoot effects only occur during the turn, so now we are wings level. The compass reads our actual heading.
Okay.
When turning to a heading near north, we undershoot. To a heading near south, we overshoot.
Okay.
For east and west, the compass reads correctly and no adjustments are needed. Now make another left turn to west, heading 270.
270.
Simply roll out on west as you see your compass near 270. And back to wings level.
Okay.
See how on heading west, the compass requires no undershoot or overshoot. This is also true for heading east.
Oh, cool.
However, when flying east or west, another acronym comes into play. Accelerate north, decelerate south, ANDS. This means that whilst on a heading of east or west, airspeed changes now cause the compass to misread. Maintain heading west and cut the power to slow us rapidly. Keep an eye on the compass. See how the compass indicates an error towards south. This is caused by our deceleration.
Let's trim to 65.
Try to maintain 3,000 feet during this exercise.
3,000 feet?
Okay, now go to full throttle to accelerate. We now see the compass show an error to the north. Accelerate to 90 knots.
All right. This is a little bit annoying. I don't want to climb anymore. I need to...
Try to maintain 3,000 feet during this exercise. reset our cruise RPM. This should highlight the importance of stable flight when relying upon the compass, as speed changes can cause significant misreadings.
Okay.
When we accelerate, the compass moves north. When we decelerate, it moves south. And when turning south, we overshoot. This means we turn beyond compass south, again by about 30 degrees. This will be our next demonstration. Start a left turn. Now keep the turn going and monitor the compass. Overshoot south by 30 degrees, so roll to wings level as the compass indicates 150. The compass is showing south, but we're going to overshoot by 30 degrees. Keep turning. Now roll wings level. Here we are heading south.
Oh, cool.
The 30 degree under or overshoot is a rough figure and is dependent on our latitude.
Interesting.
And also depends on our target heading. The number of degrees to lead or lag our target reduces to 0 as we near east and west, as we saw earlier. For example, to turn to heading 045, we may only undershoot by 15 degrees, rolling wings level when we see 060 on the compass. The accelerate north, decelerate south has the same effect, where it is at its maximum on east and west, but reduces to 0 at the poles.
Very cool.
But once again, these speed effects can be disregarded as long as we are keeping a steady speed. Let's try one more. Turn to the right this time to heading north. We will undershoot north, so roll out as the compass indicates 330.
Okay.
We will try to be very accurate with this turn.
All right. And then 330, we start to roll out. All right.
We rolled out not quite on north. Make a heading adjustment as needed.
Oh, wow, that's way off. Wow. Gonna overshoot.
We are now on heading north. Undershoot north, overshoot south applies to the northern hemisphere. In the south, these effects are the reverse. For example, if flying in New Zealand or Australia, we must overshoot north and undershoot south. Onus.
Very cool.
We will now move on and graduate to a more modern avionics suite, known as glass cockpit.
Very cool.
Be sure that you are comfortable with the Cessna 152 before we move on to the next aircraft.
Thank you. Yes. Ah. Come on. It's still a C. All right. Well, this was a pretty informative lesson. This was more learning to fly when your instruments are out or maintain your course and heading, altitude, using other information or making correction. What was also pretty cool, you can break the VSI if your static port is broken or stuck. So that was pretty interesting. So thank you very much. We're going to leave it here. I don't want to overdo it, and but I really appreciate your time and effort in joining. And if you also have any questions, anything you're more interested in learning about that I can probably try, then let me know. And thank you very much again, and have a good one.